Hi, good evening, everyone. Welcome to our May dinner meeting. Some people are still logging in, so we're going to give everybody a few minutes, and we'll be starting at 5:10 this evening. So stay tuned. Okay, looks like everybody's joined. So again, welcome to the May dinner meeting. We're so excited to have you here. So before we begin, want to first thank all of our sponsors, our Tier 1 leaders, Carrier, Con Edison, WSP, CDE, SRS, our Tier 2 partners, Train and Fulcrum Group, Goldman Copeland and Tech Systems, JB&B and Fleet, AKF and Siska Hennessy, Technical Air Systems, Johnson Controls, Belimo, and our Tier 3 supporters, Federal Pump, ADS, Chimney Design Solutions, National Air Filter, Victaulic, Schneider Electric, Siemens, Cerami, Daikin, Thermal Systems Associates, EcoCare Corp, Skyline, Rath, Wells Jarby, Wallace Ennis, MPM Boilers, LFS Systems, and I would like to take a moment. Sorry, apologies for the barking dog. I would like to just take a moment to thank all of our past presidents on this call and that continue to support and be involved in our chapter. We're very grateful for everything you bring to the chapter. And I'd also like to welcome our new members. We had a very exciting month for members joining. So welcome to those that are on the call that have joined this past year, especially in this past month. And hopefully next year when we will have in-person programming, we'll be able to meet all of you in person. A few other announcements include we are doing an IAQ community showcase for our newsletter. So if you would like to submit something for the newsletter, please send it to our ASHRAE Gmail account. It's ashraeny@gmail.com, and you'll be featured in our newsletter. Also, if you are interested in joining and participating in one of our committees next year, please reach out to any of us currently on the board or the incoming officers, and we'll be glad to help you. And we would also like to thank all of you for being wonderful members and continuing to engage with us during this very interesting year of virtual programming. We do hope to go back to in-person programming sometime next year, and we'll get to see you again and talk to you. All right, now on to tonight's presentation. I'd like to welcome Alex Garcia and Robert Middleton from RRT Design and Construction. Alex supports RRT's engineering and plant commissioning teams, and he's working on activities across waste management processes, energy generation facilities, and battery storage. Robert supports project development and management for industrial electric power systems and is experienced in all aspects of detailed engineering design for electrical power distribution systems. So welcome. Alex, I'm going to turn it over to you so we can start tonight's presentation.
All right, great. Thank you, Natalie. Let's just get set up here. All right. Hi, everyone. As Natalie said, I'm Alex Garcia. Today, I'm going to be presenting on battery energy storage. We'll be discussing multiple topics, but pretty much the underlying message here is how are we going to power our future responsibly? So let's go ahead and just dive right into that. So first, let's talk about what ESS is. So ESS stands for Energy Storage System. Now, the purpose of an energy storage system is to ensure the continuity of energy supply and improve the reliability of the system. In other words, this is just to make sure that we have our power when we need it and to avoid disruption to that power as much as possible. So there are multiple types of energy storage systems. Here I have listed 8. We have pump storage, hydropower, compressed air, molten salt, lithium-ion battery, lead-acid battery, flow battery, hydrogen, and flywheel. Now, for this presentation, we're not going to have time to cover all of these, but we will cover a few of them just to give an idea of these different types of energy storage systems and how they work. So the first two we're going to cover is compressed air energy storage and hydrogen energy storage. Now, compressed air energy storage uses excess energy to compress air into a reservoir. The reservoir can be a cavern or a container. Typically, it is a cavern in industry. Now, when energy is desired, the high-pressured air is released from the reservoir and heated and passed through a gas turbine to generate electricity. Now, you can see that there's electricity both at the beginning and end of this figure. This is just to, again, illustrate that electricity can be used, and whatever excess we have can be then sent back to the beginning of this process and used to store more compressed air and release as needed. Now, on the other hand, we have hydrogen energy storage. Hydrogen energy storage uses chemical potential energy to store hydrogen. Now, hydrogen is then released through a fuel cell, and the fuel cell will generate electricity. The electricity is used as needed, and the excess energy is then used to invoke electrolysis within water to then generate more hydrogen. And this process will repeat itself as needed, and of course, if hydrogen runs out and you use up all your energy, then a different source can be introduced to continue the process. Now, in the U.S., the most popular method of energy storage is pumped storage hydropower, and one of the most prevalent examples of that is the Hoover Dam. I'm sure everyone here has either heard of it or maybe has even visited, but the Hoover Dam is a very large example of what hydrogen pump power has to offer. So let's discuss what that is. So pumped storage hydropower has an upper reservoir and a lower reservoir of water or of some other liquid. But in most applications, it is water. So what happens is the upper reservoir is going to release water down to the lower reservoir, and in between those two reservoirs will be a turbine. The turbine will generate electricity as water flows through it. Electricity is then sent out and used as needed, but the reverse can be done as well, same as those other two energy storage system examples that we had. So in this case, when we have excess electricity, we then pump water back up to the upper reservoir and then release it again as needed. So you can see from these three examples that it's a very similar concept of using some medium to release energy, and then a similar medium to then store that energy. So now that we've discussed a few energy storage systems, I have a table here that helps to easily compare multiple energy storage systems in terms of different characteristics. So first, we have the power rating, we have discharge time, the lifetime or max cycles, the energy density, the efficiency, and the risk of thermal runaway. Now, I just want to note that the risk of thermal runaway is something we're going to touch on later. So for now, just take it with a grain of salt of whether or not a system has to deal with that. So for pumped storage hydropower, we see that the power rating is 3,000 megawatts. If we compare that to hydrogen or to compressed air, it outperforms it by a lot. Moving over to discharge time, we see that the discharge time is about 4 hours to 16 hours. This is a fairly long amount of time, especially when you compare it to hydrogen. Hydrogen takes a few minutes to a few weeks. Now, I want to point out that few weeks is really because you can slowly dissipate your hydrogen flow, but typically in applications where energy is needed quickly, you're going to utilize that quicker discharge. So going back to the pumped storage hydropower, we have the lifetime of about 30 to 60 years, which is a fairly long amount of time, again, compared to other energy storage systems. One of the downsides of pumped storage hydropower is the energy density. It has the lowest energy density of the options in this table. So that's going to be one of its biggest issues, and will lead to why we're moving away from pump storage hydropower. Just one last note regarding that is the efficiency. Their efficiency is fairly high for the system. You're getting between 70 to 85% efficiency, which overall, again, in comparison to other energy storage systems, is not bad. Now, what I want to do is move towards the lithium-ion battery, which is the main topic for this presentation. But first, I want to compare that to pump storage and kind of give an idea why the market is moving towards that. So right off the bat, you see that power rating for a lithium-ion battery is much less than a pump storage hydropower, and that's well known. But it's not a main it's not a big concern, and we'll cover why. So in the next column, you see that the discharge time is between 1 and 8 hours. So having that short of a discharge time is extremely helpful in reaching that goal of what an energy storage system is, which is to ensure the continuity. One of the issues that pump storage hydropower faces is that it takes a long time to generate the electricity needed. So even though you have a lot of energy that can be produced, if you can't have it immediately, it causes disruption to the system. In contrast, lithium-ion battery has a very fast discharge time, which will allow more reliability and more responsiveness to the system. Moving over to the next column, we have the lifetime, and in this case, we're comparing two different types or two different units. So we have years and cycles. For the battery, we have between 1,000 and 10,000 cycles, and that'll be roughly 20 to 25 years, which will be an item that we cover further in later slides. For hydropower, we have 30 to 60 years, so it does outperform lithium-ion battery in that respect, but we'll see more positive characteristics for lithium battery in just a few columns. One of the biggest positive characteristics for lithium-ion battery is the energy density. We see that lithium-ion batteries have the second highest energy density on this table. It's only second to hydrogen. Now, lithium-ion battery is 200 to 400 watt-hour per liter. This is going to be crucial in comparison to pump storage hydropower, because one of the goals or one of the reasons for moving towards lithium-ion batteries is because we want to have a smaller footprint. Having a much higher energy density will allow us to do that. In the following column, we have efficiency, and we can see that lithium-ion batteries outperform pump storage hydropower, so that's just another positive characteristic. Lastly, we have the risk of thermal runaway. As I mentioned, this is going to be a topic we cover in later slides, but for now, keep in mind that batteries will run this risk, and in other energy storage systems, this is not a concern, except for in the batteries case. So we'll move forward here and talk about lithium-ion batteries. So what is BESS? So BESS stands for Battery Energy Storage Systems. A battery energy storage system is the application of specially developed batteries to store an electric charge in order to discharge as needed. Now, one of the reasons why this is becoming prevalent in the United States is due to the desire to utilize cleaner and more efficient means of energy storage. As I mentioned in the previous slides, some of the largest or some of the best characteristics for a lithium-ion battery has to do with its discharge time, its lifetime, its efficiency, and the energy density. So here we have a figure similar to our other ESSs that shows the energy flow. So for a typical energy storage system, you'll have energy flowing in from a solar panel or the grid, which will be sent to the home. And in this example, to the home appliances. Any excess energy is sent to the battery. As you can see, there's inverters in between. That's because power to a home needs to be AC, but the power that's coming from solar panels and that it discharges from the battery is DC current. So that's the reason for the inverters in between. But really the main purpose of this figure is just to show that it is a similar concept to the other energy storage systems that we talked about before. Again, utilizing some medium to send electricity to a home or to some sort of storage, and then release it as needed. Now, I want to discuss theoretical versus practical. Now, the chart or table that I showed earlier showed that the lithium-ion batteries have a cycle between 1,000 and 10,000 cycles. Now, theoretically, yes, they can achieve this 8,000 plus cycles, but realistically speaking, what's going to determine whether or not a lithium-ion battery is used is its retention capacity. In industry, the retention capacity would not in industry, but realistically, the retention capacity will decrease over time. The industry standard for when to replace a battery is 70 to 80%. Now, from here, the question begs, well, when or how long does it take for a battery to reach 70 to 80%? Oh, excuse me. So here's a figure that shows the retention capacity and the number of cycles and how it is affected by the state of charge range. You can see that the optimal setting, according to this graph, is that a battery state of charge at 20 degrees Celsius is between 75 and 65%. This means that at most it is charged up to 75%, and the discharge should not be less than 65%. Now, this can lead to very long cycles, which is why I mentioned that theoretically it can go very far. But realistically, industries and users are not going to be using a battery between 75 and 65%. If you want to use a more common example or more personal example, if someone was to tell you to use your cell phone between 75 and 65%, I mean, I know I wouldn't be able to do that. So even if I was told that a battery would last for 20 years, if I did that, it just wouldn't work out realistically. So a more realistic setting would be between 75 and 25%. The downside of this is that you get less cycles out of it, but you're still achieving over 5,000 cycles, which 5,000 cycles over the course of 365 cycles a year will give you about 13 to 15 years worth of life before getting below 80%. What you can notice in this graph is that most of these lines actually don't reach 80%. So if we were to interpolate off the graph, we'd actually see that it goes further. But just for the sake of going off of what is on the graph, I think it's best to say that we're ending at 5,000 cycles. So for industry purposes, the best thing to do is to determine how much demand of energy you'll need. So if you are capable of having a shorter discharge and charge, such as that 75 to 65%, then utilize that, and you'll have a battery that lasts much longer. However, for more cases and cases that we see going on right now in the United States, we see more cases where where industries are using 75 to 25% and achieving that 15-year mark. And the next slide will show an example of that. So here we have an example based on some public information from Tesla. You can see that Tesla has a warranty for their Megapack for up to 15 years or 20 years if the capacity maintenance agreement is used. Now, the main purpose of me putting this here is just to show that this is an example of what's going on in the real world. We have a warranty of up to 15 years, which is what Tesla is expecting their battery to last. The 20-year mark is if they provide extra assistance in order to make sure that you have that state of charge range in order to increase the longevity of your battery. And as I mentioned earlier, this 15-year mark, it correlates over to that 5,000 full cycles. To be exact, it's 5,475 full cycles in a year. Now, I just want to quickly show that different lithium-ion batteries have different chemistries. Here are 3 examples. We have lithium, nickel, cobalt, aluminum oxide, lithium iron phosphate, and lithium titanate. Now, the purpose of showing this is just to show that with different chemistries, you get different characteristics. So with lithium, nickel, with lithium nickel cobalt aluminum oxide, you get a lower cost, but you get decreased safety. Yes, this is paired with more specific energy and a fairly long lifespan, but for different applications, you need to keep in mind what's more important here. If you're in a very tight area, maybe you want to utilize more safety and take on the cost of less specific energy. In the other two examples, we just see that a higher cost can lead to more safety, or a lower cost can lead to a longer lifespan but lower specific energy. So really, it's important to do research on the type of battery you need and what are the requirements in order to pick the best one for a project. So now let's talk about some pros and cons of lithium-ion batteries. So the pros include a decreased discharge time, increased lifetime, and referred to as max cycles, increased energy density, and increased efficiency, and the fact that they're recycled. I mentioned earlier that the retention capacity is what's going to limit a battery, and in terms of how long it's going to last, because once it reaches that 70 to 80%, it's going to be replaced. One of the great things about these batteries is that even though it reaches that point and needs to be replaced, it can have a second life in another application as long as the correct power ratings are achieved. Now, some cons of lithium-ion batteries energy storage is the risk of thermal runaway, which we'll be covering in the next slide. Well, lithium-ion batteries have a bad reputation of being expensive, but we'll cover later that that the price has been decreasing over the past 10 years, which has been a major positive for lithium-ion batteries. Next, due to that expensive cost initially as research was being done, there was a lot of limited testing. So most of the testing done has been in recent years, but there's still much to be done. And lastly, we have a physical limitation, which is the elevation limit. Most manufacturers will have a limit of about 2,000 meters above sea level. After that level, you start to run into some issues with the capabilities of the battery energy storage system. So now we can finally cover thermal runaway. So thermal runaway is when the internal generation of heat exceeds the rate of heat dissipated. This causes the resistance to decrease, which causes the current and power to increase. Some possible causes for this is external heating, overcharging, and improper handling. So again, to reiterate those causes for thermal runaway, we have external heating, which can be due to a fire or due to improper cooling. We have overcharging, which is exactly what it sounds like. We have too much charge being sent into a battery, causing increased heat due to increased current. And then we have impact, which can be as simple as dropping a battery. So when installing a battery, it's very important to treat it very carefully, because any damage, such as dents to the side of a battery, can result in damage to the separator plate within the battery. And if there's damage to the separator plate, you'll have issues regulating current, which could then lead to more temperature that will increase outside of its operating temperature and lead to thermal runaway. So now let's talk about some prevention for thermal runaway. First, we have regularly scheduled maintenance. Next, continuous monitoring and battery cabinet temperature of individual battery terminals. This is making sure that the temperature and current is within range, within the expected range. Next, we have using specially formulated lithium-ion batteries with higher resistance to thermal runaway. This ties back to the images I showed earlier, showing that different battery chemistries can have more resistance to thermal runaway, which had to do with higher safety. And lastly, we have fire detection and suppression system. So now let's discuss some fire hazards. Now, the benefit of increased energy density is paired with the increase of fire. By understanding the risk of fire, improvement toward fire detection and suppression can be made. Examples of detection methods include smoke detectors and/or aspirating smoke detectors. Examples of fire suppression include inert gases, water spray foam, and water mist systems, which we'll cover in later slides. Inert gaseous systems. An inert gaseous system uses natural extinguishing agents such as argon, carbon dioxide, and nitrogen to flood a system at risk of fire and thermal runaway. The presence of an inert gas displaces oxygen, which fuels a fire. Natural extinguishing agents are used for lithium-ion batteries instead of chemical extinguishing agents due to the risk of hazardous decomposition products that may form. Now covering those the different types of water spray, we have a typical water spray system, which releases water via a sprinkler system. The benefit of doing this is that you get direct flow to a specific area. Next, we have a foam system. It's typically used on a flammable liquid fire, where flammable liquids are more buoyant than water. Next, we have a water mist system, which has better heat absorption than typical sprinkler systems due to small particle size and higher surface area. This is typically useful for places with limited access to water. So improvements to fire prevention and suppression. The combination of inert gases extinguishing and aspirating smoke detectors are used to effectively detect onset thermal runaway and to react to potential fires. So what an aspirating smoke detector does is sample the air for electrolytic vapors. If an electrolytic vapor or gas is present, it will initiate the extinguishing system automatically. This will avoid the thermal runaway, and well, as simple as that, it will avoid the thermal runaway. Now we've covered some different fire hazards and different ways to suppress and protect from it. Now we are given fire codes from the FDNY and the NFPA. They provide fire codes for battery energy storage systems that address requirements such as testing, clearance requirements, and fire protection/detection. FDNY also provides requirements involving the setback each battery cube must have to the property line. Next, let's quickly touch on battery energy storage containment and HVAC. Now, typically the batteries are going to be contained in a cabinet or in a storage container unit. HVAC is going to be included with these units, at least in all the cases that I've seen. And these are going to be necessary for regulating operating temperature and also necessary for ventilation, because if a battery is releasing inert gases, we cannot allow that to be contained in a unit. That has to be discharged properly. So now the importance of thermal management. The batteries have a small range for the operating temperature, which is between 20 to 25 degrees Celsius. Deviation from this range will cause cells to degrade or catch fire. Undersizing the cooling system can lead to batteries overheating. Oversizing the cooling system can lead to short cycling of the cooling system and large air temperature swings when the unit turns on and off. Now, trying to tie what we discussed to this point to New York State, we know that in 2018, Governor Andrew Cuomo announced the nation-leading goal of 1,500 megawatts of energy storage by 2015 and 3,000 megawatts by 2030. So, yes, there are a lot of benefits to lithium-ion battery energy storage, and yes, there are reasons to go for it aside from the incentives, but in New York State they are pushing for it. So a lot of the incentive right now is due to the statewide push for it. Now, the amount of incentives that we're given is about $350 million in order to accelerate the energy storage market. Groups such as NYSERDA and the New York State Department of Public Service, DPS, has developed roadmaps to identify a promising near-term policies, regulations, and incentives needed to achieve the 3,000 megawatt goal. Now, here's an example of a guideline that NYSERDA has put together. The purpose of the guideline is in order to show the authorities that need to be the authorities that need to be contacted, the forms that need to be put together, and the order in which these forms need to be put together. And NYSERDA also provides this next guideline, which shows, again, the order in which the forms need to be shown. This is more of a broad overview, but in the NYSERDA guide, they actually show individual documents and also where to submit the documents. So it's a very helpful document for understanding the battery energy storage approval process. Now let's go over the future of battery energy storage. Well, I mentioned earlier that there has been a decrease in the cost of lithium-ion batteries, and due to this increase, there's been an increase in the production of lithium-ion battery energy storage, and also an increase in testing. The increase in testing is extremely important, both in understanding lithium-ion batteries and how they work and looking at ways to improve them, but also in determining issues with safety. So testing can be used to understand how fires form, signs for thermal runaway, and also how the height of fires as well, which again is important in understanding clearance requirements and any additional fire protection or suppression that's needed. So by 2030, stationary and transportation energy storage combined markets are estimated to grow to 2.5 to 4 terawatt hours, which is, I mean, that's an incredible amount, especially compared to where the market is as of December 2020, which is 800 gigawatt hours. Continued research on battery energy storage with the expectation that batteries will be capable of smaller footprints due to higher energy density, which that's the underlying goal of the research for battery energy storage, is to get to achieve smaller footprints, but also to achieve more safety. Now, to reiterate what I've mentioned before about lithium-ion prices, we see that in 2010, the cost of a lithium-ion battery was nearly $1,200, and every year since has decreased fairly dramatically. And in 2020, the price is $137 per lithium-ion battery. Now, this is incredible for the industry and will allow the industry to be more available to different uses. But the thing is, there are still changes that may occur, such as the lithium shortage that has recently occurred. Many of you may be actually aware of it, but things like that may hurt the industry. So this price may end up going up for the first time in the past 10 years, but still the prices are very low, and it's a very good sign for the industry in the future. So that wraps up what I have for the presentation today. Thank you everyone for listening. I'd be happy to answer any questions.
All right, great. Thank you, Alex. Okay, so to give everybody a moment, you can just add your questions to the questions box, and I will read them out loud. While you guys are doing that, I just wanted to remind everybody, when you exit the webinar, if you require PDH credits, please make sure that you fill out the survey, so that way we can log your attendance and issue you a certificate. All right, so let's get started with some questions. First question is, where are lithium-ion batteries recycled?
Where are they recycled? That's an excellent. Sorry, I don't happen to know exactly where they're recycled. Robert, do you have any insight on that?
Lithium is going into recycling markets, similar to other metals, and so you can pretty much go on the internet, find a recycler for metals, and they're entering the lithium recycling just like other metals.
Okay. I'm sorry, Robert, did you want to add something else?
No, that's it. It's just similar to other metallic metals, whether it be iron, copper, uh, you know, aluminum. These metals are going to recycling market.
Okay. Next question. Are there any lithium-ion batteries approved for indoor or rooftop high-rise installations in New York City?
Well, the short answer is yes. They have been approved in New York City. Robert, have you actually? I don't remember any examples off the top of my head, but I do remember reading different examples of rooftop, and I know that a lot of the regulations we receive I'll constantly ask about that, whether or not we're placing these on rooftops or on ground level.
There are. I do know of current projects that are being rooftop battery energy storage projects that are being currently permitted. I don't know if any are in current operation, but they are going through the permit process. A couple of projects.
Okay, great. Next question. In residential projects in New York City, are there any updates when battery energy storage will be permitted?
Not that I have. I don't have any updates, but I do know that from the research that I've seen that the battery energy storage market is very much encouraging people to get battery energy storage systems for their houses. One in particular is Tesla. Tesla is really looking to make a name for itself for battery energy storage within homes.
There are a number of I can't say specifically to lithium ion, but there are systems for battery storage for backup power in residential. I think the ones that I'm very familiar with are still lead acid, but you know, I do know Tesla does offer a system that is lithium ion for the home. The current ones that I know that are installed are lead acid battery systems. They'd be installed in like a garage at the home.
Yep, or the side of the house. There's some examples that I've seen. They're very compact units.
Okay, next question. They would like to know, are lithium-ion batteries made in the United States or China?
Both. Yeah, no, we have. I mean, Tesla would be an example of an industry utilizing batteries manufactured in China, but also having their own manufacturing here in the United States. But another example of a very large battery energy storage, or sorry, a large lithium-ion battery manufacturer is KLTL. Sorry, not KLTL. It's CATL.
Okay, great. When the BESS automatically discharges fire suppression, does it also shut down?
In some cases, yes. Yes. So if the battery energy unit, battery energy storage unit detects an issue that can range from a fire or even a leakage, it is the battery cube itself, not necessarily the string of batteries, will shut down. But if the unit is designed to otherwise handle it in an individual basis, it won't shut down the entire string, which is I think it's an important differentiation.
Are BESS acceptable for an emergency standby power source in New York City? Is specific approval by the FDNY or DOB required?
Yeah, battery energy storage is being looked at as a backup power source in New York City, and no matter what the case, the approvals through both Department of Building and FD&Y is always required. But the applications do include backup power sources.
Okay, great. When managing thermals for a BESS, are there considerations that need to be made for the environment, i.e. direct sunlight, desert, etc.?
Sorry,
Yeah,
go ahead, Rob.
as Alex indicated in the presentation, the operating temperature range of a battery system, and any battery system, its production and capacity is related to temperature. So if it's in a right now I'm sitting in Texas where it's nice and warm. If it's in a hot location, it's going to tend to heat up more and have the output of it's going to be restricted by the increased resistance of the system, and therefore reduced output. So it is sensitive to environmental conditions, yes.
Okay, just comment from one of our members for recycling to follow up on the previous question about where can they be recycled. Carson City, Nevada has a company called Redwood Materials. So thank you for submitting that follow-up response to us. Okay, next question. According to publicly available NYSERDA data, there are no lithium-ion battery energy storage projects projected for Manhattan installations, particularly on or in high-rise buildings. Do you foresee any market change that will occur?
For battery storage in New York City, was that the question?
I kind of butchered the end of it. It says, do you foresee any market changes that will change this?
Not market changes, yes, but in the near term, the evolution is going to be driven by the mandate that Alex mentioned in his presentation to push battery storage to 1,500 megawatts by 2025. There is resistance in the city of New York because the state can achieve that goal without really going into New York City. But as these systems become more prevalent, the market's going to drive itself, and I believe New York City will eventually adopt battery storage just like the rest of the state.
Okay. In earlier 2020, Tesla was not pursuing UL 9540 and UL 9540A testing, prohibiting their product to be installed in NYC. Doesn't meet FDNY and DOB requirements. Has that changed as of today?
Robert, correct me if I'm wrong, but haven't they recently gotten the UL listing? I thought.
Tesla, the Megapack systems have over the last couple of years. I'm not sure when it started, but they have qualified UL 9540, and the systems have been tested and performed for 9540A testing, and those certifications are required for any projects for any project to get FDNY, Fire Department of New York permitted.
Okay. Other than Tesla, what other lithium-ion batteries are approved for installation in New York City?
Well, I mean, Robert, the first answer would be Fluence, right?
Yeah, we're working on the Fluence system, which is a Siemens product. We've also worked on FlexGen systems. We've also NEC is a product that they kind of left the business a while back ago, but it was another different system. So they're a plethora of different products coming on the market, and which ones kind of get first mover status. I'm believing that Fluence and Tesla are presently showing the most activity that I can see.
Okay, great. Lithium mining energy sorry, let me restart this question. Is lithium mining energy intensive and environmental friendly?
I really don't know about the mining of lithium myself, but I will say that generally when you're talking about mining, it's not necessarily all that environmental friendly. Even when you're doing crypto mining, it's not so environmental friendly, and it's not even digging anything out of a mountain.
Okay. Can you speak to how lithium-ion batteries compare to zinc hybrid cathode batteries?
Alex had a slide that showed some comparisons. I don't know, Alex, you got something on that?
I don't believe it didn't compare to zinc. Compared to say lithium, nickel, cobalt, aluminum oxide, and lithium titanate. So I can't speak towards the zinc hybrids. I did a little reading on those, but to be honest, I don't have a concrete answer for that.
Okay. That is all the questions that were submitted by the audience. I'll just give you guys a minute in case there's any additional questions, but I'd like to thank Alex and Robert for joining us today and presenting on this new technology that's emerging for us. We very much appreciate it, and I'd like to thank everybody for attending. We look forward to seeing you in the fall. Oh, we have one more question. For high-rise projects with a rooftop battery energy storage, DOB FDNY require third-party deflagration calculations from an engineer. Is this a typical requirement that you have seen?
Repeat that again. Did you say FDNY require what?
Yeah, DOB FDNY require third-party deflagration. I might be pronouncing that wrong.
Oh.
Calculations from an engineer. Is this a typical requirement that you have seen?
In the permitting for the project, yes, that is a requirement to submit the defragmentation, whatever calculation. I don't know if it's required to be third party. I'm thinking it's typically submitted by the manufacturer.
Okay. I'll give everybody a last call. Okay, it looks like that is it. So again, thank you, Alex and Robert, for joining us this evening. Remember, if you need PDH credits, please complete the survey upon exit of the webinar. If you don't receive it, please just reach out and we can confirm your attendance. That way we'll ask you for some information. And again, thank you for joining us, and we look forward to seeing everybody in the fall.
Great. Thank you, Natalie. This is it's been our pleasure. Thank you for having us.
Thanks, Natalie. Thanks, Alex, for putting it all together for us.
Of course. And thank you everyone for your comments. I mean, I've taken note on them. These are all really helpful. So thank you.